Hello my dear children, welcome to another wonderful session of digital classes. In the last session we have discussed reflection of light at curved surfaces and the loss of reflection at the curved surface, isn't it? Today we are going to learn another interesting phenomenon of light. Are you ready, students? Right. Dear students, did you remember a very famous rhyme when you were in kid? Twinkle twinkle little star, that what we were taught. Do the stars twinkle really? No. Then what is the optical phenomena behind the twinkling of the stars? Do you know the reason? Yes, that is because of the refraction of light. My dear students, see this picture carefully, the broken pencil. Dear students, you can see the spoon appears to be broken at the surface of the water. What could be the reason? Yes, again the reason is refraction of light, isn't it? Dear children, so far we have learned the refraction of light only across the plane surface. Is it right? Let us try to recapitulate what we have learned in our early classes related to refraction of light at plane surface. Ray of light through a homogeneous medium. Dear students, observe this picture. The light is travelling in a straight line. Why? What could be the reason? Because it is a single medium. So, light travels in a straight line direction provided there is no change of medium. Dear children, do you know what is a transparent object or transparent material? Yes, very good. The objects which allow the light to pass through them are known as transparent materials. Can you able to tell some examples of transparent materials? Yes, good. Glass, water, kerosene, air, these are all the transparent materials. So, what are transparent materials? The materials which allow the light to pass through them are known as transparent materials, right? Objects like water, glass are transparent because they will allow the light to pass through them. And what happens if the light travels from one transparent material to another transparent material? Let us see with an interesting activity. Take a transparent glass and fill it with water, dip some portion of pencil vertically in water and observe. Then keep the pencil inclined to water surface and observe. What do you observe? In the second case, the pencil appears to be broken near the surface of water, isn't it? Take a transparent glass and fill it with water, dip some portion of pencil vertically in water and observe. Then keep the pencil inclined to water surface and observe. In the second case, the pencil appears to be broken near the surface of water. Why does it happen? Let us know with the ray diagram. Dear children, let us see the explanation for the previous activity with the help of a ray diagram. In the first case, when the pencil is dipped vertically from rarer medium to denser medium, when light passes from rarer medium, dear children, tell me in which direction the refracted light ray is going to bend. Is there any bending? No, because the light is going to incident normally. So, according to Snell's law, which is considered to be the laws of refraction, it is not going to deviate. So, the refracted light ray passes into denser medium without any deviation. So, the ray travels without deviation, whereas I is equal to 0 and R is equals to 0. Dear students, in the second case, rarer medium and denser medium, the light is travelling from rarer medium and rather normal at the interface. The light is going to incident with an angle of incidence I. See the children, in which direction the refracted light ray is going to bend? Yes, good. This is a denser medium, that is why the light ray is going to bend towards the normal. Here the angle of refraction is R. Now, here the laws of refraction are holds good. According to Snell's law, the angle of incidence I and angle of refraction R are not equal. So, according to Snell's law, n1 sin I is equals to n2 sin r. Dear students, this is all about the refraction of light at plane surfaces. Children, now let us try to define what is refraction of light. Refraction of light. When light travels from one transparent medium to another medium, its direction changes at the interface. Dear students, this is all about the refraction of light at plane surfaces. Now let us try to watch some interesting pictures. Are you ready? Dear children, see the beautiful image of sunflower inside a glass sphere. Observe the lenses in binoculars. Oh, what a beautiful droplet on the surface of a leaf. The watch glasses, that where you can watch it in your chemistry lab. The spectacles and a magnifying glass. Dear students, what is the common feature among all these images? Yes, all those are transparent materials. Is there any common feature among all these images? Yes. Are they plane surfaces? No, they are curved surfaces. So, now our topic is how the light is going to refract at the curved surfaces. So, let us try to understand how the light is going to refract at the curved surfaces with an interesting activity. Are you ready? Dear children, take a piece of paper and draw two arrows in the same direction, and take an empty glass tumbler and keep it in front of arrow. You can observe a diminished image of the two arrows. Let us try to pour some water into the glass tumbler. Observe carefully. Oh, it is interesting. The lower arrow gets inverted. What could be the reason? If you see through air, the two arrows are pointing in the same direction, whereas if you observe through the glass, the lower one gets inverted its direction. Dear students, from the previous activity, can you tell what is the reason for the inversion of the arrow? Lower arrow gets inverted. Can you guess what is the reason? You can find the answer after the discussion of refraction of light at curved surfaces. Before going to learn the refraction of light at curved surfaces, let us try to introduce what is actually a curved surface to a light ray. Curved refracting surface. Dear children, see, this is a transparent glass paperweight made up of glass and which is placed in air. Now allow a light ray which is going to fall on a transparent glass sphere. The light ray has to hit the surface. Where the light ray is going to hit the surface, is it a plane surface or a curved surface? Definitely it is not a plane surface, it is a curved surface. You can see the curved surface. So, for this light ray, this surface is a curved surface. So, now we have to discuss how this light ray is going to refract. The interface of air and glass here is a curved surface. Dear children, I hope you understood what is actually a curved surface as far as a light ray is concerned. Now let us try to know what are the terms involved in curved refracting surfaces. Center of curvature. Children, see here, this is a curved refracting surface. This is actually a portion from a sphere, the midpoint of the actual sphere from which a curved surface is a part is center of curvature. The center of sphere of which curved surface is part is called center of curvature. You can see this is the center of curvature. Now let us try to understand the remaining terms also. Now let us try to know what is a pole. Dear children, this is a curved surface and the midpoint of the curved surface is pole. It is represented with letter P. the center of the curved surface is called the pole of the curved surface. You can see this is the pole of the curved surface. Principal axis. See the children, this is a curved surface, P is pole, C is center of curvature. The line which joins pole and center of curvature is principal axis. So, the line which joins the center of curvature and pole is called principal axis. You can see children, this is the principal axis. How to draw a normal to a curved surface? Students, already you learned how to draw a normal to a curved surface in case of reflection. Here similarly you can draw normal to a curved surface. A normal is a line which is drawn from the center to the surface. This is the normal at this point, and you can draw another normal. You can draw many number of normals. Every normal should pass from the center to the point on the curved surface. You can see different type of normals here. So, the different normals at different points are shown in the picture clearly, right. Dear children, in the last session you learned how to draw the ray diagrams for curved reflecting surface. Now, in this class we are going to learn how the ray diagrams are going to be drawn to a curved refracting surface. Normal incidence. If you take a curved refracting surface separated with rarer and denser medium, refracting surface is made up of denser medium. See the light ray children, this is going to pass through the center of curvature. So, this light is going to incident normally. Is there any deviation for this light ray? Let us see. Oh no, it is going to pass through the denser medium without deviation. See the another light ray, again which is going to pass through the center of curvature, it is also not going to deviate. So, in this picture these two light rays are going to incident normally on the curved refracting surface. Here angle of incidence is 0 and angle of refraction is also 0. Dear children, let us see what happens to a light ray when it is going to incident parallel to the principal axis. Convex refracting surface, a ray travelling parallel to the principal axis. This is a curved refracting surface which is denser medium with refractive index N2, and another medium is rarer medium. If a light ray is going to incident parallel to principal axis, draw the normal at this point, angle of incidence I. Then in which direction the refracted light ray is going to pass through the denser material? Yes, it is going to bend toward the normal as the light is going to enter into the denser medium. Here angle of refraction is R. Will the laws of refraction valid in this case? Yes, even for a curved refracting surface also the laws of refraction, that is Snell's law, is applicable. It follows Snell's law, N1 sin I is equals to N2 sin R, and the ray bends toward the normal. See the next case, concave refracting surface, the ray travelling parallel to principal axis. This is a concave refracting surface for the light ray which is coming from denser medium and entering into rarer medium. So, draw the normal at this point, angle of incidence is I and the refracted light ray is bending away from the normal and it is going to touch the principal axis at one point. It follows Snell's law, N2 sin I is equals to N1 sin R. See the next ray diagram, convex refracting surface, ray travelling parallel to principal axis. Here comes the picture. This is a rarer medium and this is denser medium. Light ray is entering from denser medium, draw the normal, and the refracted light ray is going to move away from the normal. Is it going to meet the principal axis? No. Then you extend that light ray backwards. It is going to meet the principal axis at that point. It follows Snell's law, N2 sin I is equals to N1 sin R. The ray bends away from the normal. See the next diagram, concave refracting surface, ray travelling parallel to principal axis. Again denser medium, rarer medium, the light ray is coming from rarer medium. For that light ray, the curved refracting surface is a concave refracting surface. draw the normal, and the refracted light ray is going to move toward the normal because it is denser medium. So, your anguli is more than angular and you extend that refracted light ray backward so that it is going to meet the principal axis. It follows Snell's law, n1 sin I is equals to n2 sin r. The ray bends towards the normal. Dear children, in all these 4 pictures, the light ray is going to incident parallel to the principal axis and it is going to meet the principal axis at one point. The refracted light ray, where it is going to hit the principal axis, that point is known as focal point. You can observe the focal points in all the 4 cases. Now, let us try to define what is focal point. Focal point, the point where refracted ray intersects the principal axis, is called focal point. Dear children, many times you might have seen the image of a lemon inside a glass. Have you ever wondered? The lemon appears to be bulged inside when you are observing through water and as well as glass. See the beauty of the image through curved surface. Dear children, in the previous sessions we discussed how the image is going to form. Now, here we are going to discuss how the image is going to form in case of curved refracting surfaces. Formation of image at curved surface. Here it is a curved refracting surface with 2 different refractive indices n1 and n2. Take an object O, point object, and this is the incident light ray. Draw the normal at this point and the refracted light ray is going to bend toward the normal with an angle of incidence I, and take another light ray which is passing through the pole and center of curvature, which is not going to bend, and these 2 light rays are going to meet at one point where you can get the image. This is how image can be traced in case of a curved refracting surface. In this case, the distance from P to O is distance of the object u and the distance from pole to image I is image distance v. Children, in the last lesson you learned mirror formula for curved reflecting surface. In this lesson we are going to learn curved refracting surface formula. Curved surface formula is n2 by v minus n1 by u is equals to n2 minus n1 by r. Here n1 and n2 refractive indices, u object distance, v image distance and r radius of curvature. Curved surface formula for a plane surface. Radius of curvature r approaches to infinity for a plane surface. 1 by r is equals to 0. If you substitute 1 by r is equal to 0 in the formula, you will get n2 by v minus n1 by u is equals to 0, which implies n2 by v is equals to n1 by u. This is the formula for a plane surface. That means curved surface formula is applicable even for a plane surface also. Dear children, where you can use the curved surface formula? Is there any real life application for this formula? Let us try to analyze with some examples. Example problem 1. A bird is flying down vertically toward the surface of water in a pond with constant speed. There is a fish inside water. If that fish is exactly vertically below the bird, then the bird will appear to the fish to be. See the children, here a bird is exactly above the fish. So, how the bird is going to be appear for the fish? You can see a bird and fish here. The bird is coming toward the fish. Then in the problem we have to find how the bird is going to appear for the fish. Is it going to appear nearer or farther, or will it come slowly or quickly as far as fish is concerned? Let us see with the ray diagram. The bird is in air with refractive index 1 and fish is in water with refractive index n. This is the location of the fish and the bird. Draw a light ray from the bird which is going to incident normally, so that it is going to pass through the material without deviation. Now, take another light ray, draw the normal and draw the refracted light ray which is going to bend toward the normal, and these 2 refracted light rays, this light ray and this light ray, are never going to meet to form a real image. So, what we have to do? extend these two refracted light rays backwards. This is one refracted light ray and this is the extended refracted light ray. So, these two are going to meet at this point. This is the point where the image of the bird is going to form, which is virtual. So, the fish can see the image of the bird at this point. So, children, for the fish, the bird appears to be at more distance than the actual distance of the bird. So, now you can see the bird is actually at x distance, but it appears to be at y distance from the surface of the water. Here object distance is minus x and image distance is minus y. Now, let us try to solve the problem. For a plane surface, n2 by v is equals to n1 by u, n2 by v is minus y is equals to n1 by u is minus x. So, n by y is equals to 1 by x. So, y is equals to n into x, where n is the refractive index of water. So, from this it is clear that the distance of the image of the bird is going to be more than the object distance. That means, the bird appears to be at more distance than its actual position. Dear children, let us try to apply the curved surface formula for a curved surface now. Example 2. A transparent glass sphere has a small opaque dot at its center. Does the apparent position of the dot appear to be the same as its actual position when observed from outside? See, this is a transparent glass sphere and in the problem it is given that it has a small dot. Does the apparent position of the dot appear to be the same as its actual position when observed from outside? See a dot inside a glass sphere here. This is actually a glass sphere and this is the dot exactly in the middle of the glass sphere. So, in order to see the image of the dot, we need minimum 2 light rays which are coming from the dot. Let us consider one light ray and this is the second light ray. These 2 light rays are coming from the center, so there is no deviation, but these 2 light rays are not going to meet. So, we cannot get a real image. So, if you extend these 2 light rays backwards, again they are going to meet at the same point. So, we have extended the light rays, so the image is virtual and they are going to meet at that point. Actually, they are not meeting, they are appears to be coming from that point. So, you can find a virtual image at that point. So, let us try to check the answer. Here object distance is minus r according to sign convention. So, here this is the object location and this is pole. So, light rays are coming from object. So, distance should be measured from the pole. So, object distance is minus r, radius of curvature P to O. So, that is also minus r. Apply curved surface formula. N2 by V minus N1 by U is equals to N2 minus N1 by R. 1 by V minus N by minus R is equals to 1 minus N by minus R. So, 1 plus V plus N by R is equals to 1 by minus R plus N by R. So, if you cancel N by R and N by R, you will get 1 by V is equals to minus 1 by R. So, final answer V is equals to minus R. In the beginning we considered that U is equals to minus R, that means object is at minus R distance and we got V, that is image distance, is also minus R. So, image distance and object distance are equal. So, apparent position of dot is same as its actual position. Dear children, now let us try to recollect what we have learnt today. What have you learned? We learned different type of curved surfaces, refraction at curved surface and curved surface formula with some examples. Let us try to answer the question after the completion of this lesson. What do you know about the terms given below related to curved refracting surface? Principal axis and radius of curvature. What is a focal point? Children, hope you understood the concept well. Let us try to meet with another interesting session in the next class. Meanwhile, please visit SIET official website and try to solve the worksheets given. Thank you.
స్టేట్ బ్యాంక్ ఆఫ్ ఇండియాలో ప్రొబేషనరీ ఆఫీసర్స్ పోస్టుల కోసం నోటిఫికేషన్ విడుదల. మొత్తం ఖాళీలు 2000. అర్హత గుర్తింపు పొందిన యూనివర్సిటీ నుంచి బ్యాచిలర్ డిగ్రీలో ఉత్తీర్ణత. డిగ్రీ చివరి సంవత్సరం చదువుతున్నవారు అర్హులు. ఎంపిక ప్రిలిమినరీ, మెయిన్స్ పరీక్ష, ఇంటర్వ్యూ ద్వారా. దరఖాస్తు ఆన్లైన్ ద్వారా. చివరి తేదీ 4/12/2020. వెబ్సైట్ www.sbi.co.in.
ఆరోగ్య మిత్ర. అవేక్ టెక్నిక్తో ఏ రకమైన బ్రెయిన్ ట్యూమర్లకు శస్త్రచికిత్స చేస్తారు? సంప్రదాయ శస్త్రచికిత్స పద్ధతుల కన్నా అవేక్ టెక్నిక్ ప్రాముఖ్యత ఏమిటి? అవేక్ టెక్నిక్తో శస్త్రచికిత్స చేసినప్పుడు నొప్పి ఉంటుందా? అవేక్ టెక్నిక్తో బ్రెయిన్ సర్జరీ చేస్తున్నప్పుడు పేషెంట్ను ఏం చేయమని అడుగుతారు? అవేక్ బ్రెయిన్ సర్జరీ అనంతరం పేషెంట్ ఎంత త్వరగా కోలుకుంటాడు? ఇలాంటి మీ సందేహాలన్నింటికీ న్యూరోసర్జరీ విభాగం అసోసియేట్ ప్రొఫెసర్